Okay, so now we're going to tackle rotational kinematics. So we're going to answer the questions of if I know the acceleration of something, right? And it has a moment of inertia, so it has some resistance to rotation, then how fast it will go. So it's now a SUVAT problem. So what I call it is SUVAT for rotations. And believe it or not, it's very, very simple, very much simpler. If you know how to do SUVAT for linear motions, this is just changing your Latin alphabet to Greek alphabet. That's all. Okay, what do I mean by that? All right, so first of all, what are the key players, right? The key players in the linear motion was SUVAT, right? So that is, remember, it's a linear displacement, and this is the initial velocity, final velocity, the linear acceleration and time. Okay, so for us, the time it doesn't have sort of angle or not. Time is just what formally it's called parameter, but yeah, so that stays. All right, but this time instead of saying, hey, this is x naught, and so x initial and x final, and looking at s is the, so s, right, is the displacement, final minus initial. We're looking at angle, so how much you have changed. So let's call this yeah, so usually you pick somewhere to be an origin, because this doesn't even, right, so it's xf minus xi. Let's just pull the analogy, right? You have an origin somewhere, and then you have displacement going from here to here. So you have the origin, we'll pick theta equals 0 as sort of the polar angle definition. All mathematicians sort of prefer it this way. And let's say I rotate from here to here. So this is theta I, right? The polar angle theta I, this is polar angle theta F. So this is the angular displacement, right? So theta F minus theta I, right? So unlike SUVAT, we don't have a nice invention of S. It's just angular displacement, but we're going to call it, just delta theta. And angular velocity, remember, we had defined this, right, as the instantaneous one is d theta dt. So basically the rate of change of theta as, so theta as a function of time, if you use the formal approach, or the average is just take the overall angular displacement. So this is angular displacement, and this is linear displacement, angular displacement, right? And divide by the time taken for that period. So we have omega naught, usually that's the symbol, and omega, you can just use omega or omega final, right? So initial and final like that, okay? Usually the instantaneous initial velocity and the instantaneous final velocity like this. And the angular acceleration is alpha. The definition is here. We've defined that in circular motion, just to jot your memory, right? And average angular acceleration is the change of angular speed or angular velocity over time, taken, right? So very similar, right? This plays the role of angular displacement. So this is angular displacement. This is angular velocity, instantaneous and average, and angular acceleration. Okay, and we have time. So these are the key players. And believe it or not, the SUVAT equations are exactly the same. You just have to now replace the English letters into Greek letters, and you're done. So also, first of all, remember, these only work with constant acceleration, and these equation works with, well, the variables don't work, but are more general. The variables are general, but the SUVAT equations that I'm going to write out only works for constant angular acceleration, right? And if it's constant, that means at every instant, it's the same alpha. So this is going to be, if it's constant, so if alpha is constant, then it's the same as the average acceleration. Okay, so instantaneous is equals to average if every instant it's the same. All right, so hopefully that's a quick reminder. And the kinematics equation for this, right, is so we start with what were the linear ones? Remember, the linear ones were v equals to u plus at, s equals to u plus v over 2 times t. This is basically average velocity times time. It's the displacement, or average velocity is displacement over time, and s equals to ut plus half at squared, v squared equals to u squared plus 2as, right? Hopefully it's not too long ago. So now you just have to translate it to v is omega plus omega naught plus alpha t. That's the first one. Second one is the angular displacement is initial angular velocity, final angular velocity. You can put final if you want, it's up to you. There's no standard. As far as I know, no one has invented sort of a everyone agreed upon set of symbols. So we're just going to sort of massage with the formal approach symbols, but to reproduce these equations because I have those memorized. So every time I just translate that in my head, right? So delta theta is omega naught t plus 1/2 alpha t squared. And finally, is omega squared, omega naught plus 2 alpha delta theta, like this. So it looks very unfamiliar, but basically this is what I do every time, just translate that in my head. So all the problem, I'll show you an example in a second, it's the same procedure. You write out these things, what you know and what is your aim, what is the one that you don't care. Usually you need 3 out of 5 to be able to find everything. So you write out which 3 of those you will know from the problem and pick an equation to use, right? So this one has no angular displacement. This one has no angular acceleration. This one has no final angular velocity. And this one has no time, like that. All right, so exactly the same procedure. All right, so let's look at an example, right? Let's look at if you go on a carousel, like a merry-go-round,